Welcome to the lecture on Pre-Calculus Section 3.4. This section is about finding complex zeros of a polynomial using long division. But the first part is going to be a review of operations using complex numbers, what the imaginary unit I is defined as, and how we use that in complex operations, and a review of quadratic solutions which have imaginary numbers in them. Okay, let's touch on the set of complex numbers. So the set of complex numbers is the largest set of numbers, and this set includes numbers that have a real part and an imaginary part, a real part and an imaginary part, and then it includes pure real numbers that do not have an imaginary part, and it includes pure imaginary numbers that do not have a real part, and down here, here's another one, a real part and an imaginary part. So the form that a complex number is written in is a plus bi, where a is the real number portion, b is a real number coefficient of the imaginary piece of the complex number. So think about a complex number as being a combination of real plus imaginary parts. So if you have a real number here, which doesn't have an I part, that just means that the b is 0. The coefficient of the imaginary part is 0. And if you have a pure imaginary number, which doesn't have a real part added to it, then the a is 0. So looking at this first item, number 1, this is the square root of -1. Well, this is the definition of I. So that's defined as I, the imaginary unit. So then looking at number 2, we can simplify this as the square root of -1 times the square root of 100. So that's equal to I times the square root of 100. And we're talking about the principal square root of 100, so we're not going to put pluses and minuses on these in this context. So this would just be I times 10, or we would write 10I. Okay, looking at the next one, I have 8 minus the square root of -49. So this is your imaginary part here. So we'll write this as 8 minus the square root of -1 times the square root of 49, which is equal to 8 minus I times the square root of 49 is 7. So this is going to be equal to the real part 8 minus the imaginary part 7i. Looking at number 4, this is a plus bi plus another a plus bi, so we're adding two complex numbers together. All right, so since we're adding, the parentheses don't necessarily need to be there because we don't need to do any distributing. So I'm going to take the parentheses off since I'm adding two complex numbers together. So now you can think about it as combining like terms. So I have 8 plus 6, that's going to give me my real part of the complex number. And then I have -2i plus 3i, which is 1i, so I can just say I. So this is the imaginary part of the complex number. Looking at number 5, I have a minus sign in between, so I am going to have to distribute the minus this time to both items in the second set of parentheses. I can take off the parentheses in the first one. They're not doing anything. And then distributing the minus, I have -5 plus 12i. Now I'm going to combine the real parts, so that's 20 minus 5. And I'm going to combine the imaginary parts, -5 plus 12. So now I've got a complex number in the form a plus bi. Okay, let's do one more of these. there's a plus in between these two complex numbers, so I can take off the parentheses. So I've got 24 minus, so this is going to be the square root of negative 1 times the square root of 16. And I'm going to take off the parentheses on the last complex number. So this is going to be plus minus 10. So I can just say minus 10 here instead of plus minus 10. And then I've got plus the square root of negative 81. So that's plus square root of negative 1 times the square root of 81. So now let's go down to the next line. I've got 24 minus, so this is I, and this is the square root of 16, principal square root 4. So this is 4I. Then I have minus 10. And then I've got I times the principal square root of 81, which is 9. So this is 9I. Okay, now let's combine the real parts. 24 minus 10 is 14. Negative 4I plus 9I is positive 5I. So this is in the form A plus BI. Now we're going to do some multiplication. So number 1 says negative 5 times the square root of negative 16, which is the square root of negative 1 times the square root of 16. So that's equal to negative 5 times I times the square root of 16, which is 4. So we want to put the I last, so this would be written as negative 20I. Right, on number 2, we're going to distribute. So we're going to distribute negative 6I to 4 and then to negative 3I. So let's write that as negative 6I times 4 and then plus negative 6I times negative 3I. All right, so that's going to be equal to negative 24I plus 18 times I squared. All right, now let's talk about what I squared is down here in the corner for a minute. So I squared is equal to I times I, which is equal to the square root of negative 1 times the square root of negative 1. All right? So whenever you've got the same thing underneath on a radical, so basically I've got two square root of 1's, two negative 1's underneath one square root sign. Whenever that happens, you've got two of anything, you can take one out. So I squared is equal to negative 1, and that's going to come up a lot when you're doing multiplication. So I squared is equal to negative 1. All right, so if I simplify this one more time, I've got, let's put the real part first. So this is going to be 18 times negative 1, which is negative 18. So that's going to be my real part. And then negative 24I is going to be my imaginary part. All right, let's work on number 3 now. So we're going to do some double distributing here on number 3. So first we'll distribute the 2 times 5 minus 4I. And then we'll distribute the negative 3I to 5 minus 4I. So that's going to be equal to 10 minus 8I minus 15I plus 12I squared. All right, so here's an I squared, so circle that and call that negative 1. So that's going to turn 12 into negative 12. So let's write that over here. So if I combine like terms, the real parts are going to be 10 minus 12, negative 2. That's my real part. My imaginary parts are going to be negative 8I minus 15I, which is negative 23I. Okay, one more multiplication. So here what we have is double distributing again. So this is really 6 minus 4i times 6 minus 4i. And you want to be very careful that you don't just square the 6 and square the 4i, because you'll be missing the middle terms. Okay, so this is double distributing again. So I've got 6 distributed to 6 minus 4i, and then minus 4i distributed to 6 minus 4i again. So I've got 36 minus 24i minus 24i plus 16i squared. All right, circle your I squared, replace that with -1, and combine like terms. So now my real terms are 36 and -16. So that's 36 minus 16, which is 20. That's my real part. My imaginary part's -24i minus 24i, which is minus 48i. So there's my complex number. So let's look at these powers of I here. So number 1 is I squared, because the square root of -1 is I. It's defined as I. So this is I squared. So this is I cubed. So this is I to the 4th. And this is I to the 5th. So we already talked about how I squared is equal to -1. So since this would be I squared times I, this is -1 times I, which is equal to -I. Since I to the 4th is I cubed times I, this is equal to -I times another I. So this is -I squared, which is equal to -1, which is equal to +1. And then I to the 5th is I to the 4th times another I. I to the 4th is 1 times I, which would simply be I. So I'm going to make a little table down here in the right-hand corner. I to the first power is simply I. I to the second power is -1. I to the third power is -I. And I to the 4th power is 1. And then if I keep going, I found I to the 5th power is I would start repeating this table all over again as I went 5, 6, 7, and 8. So there are 4 possible values for powers of I. So anytime you repeat this pattern, you'd be going up another set of 4. So 5, 6, 7, 8 would be the same as I to the 1st, I to the 2nd, I to the 3rd, to the 4th, and then 9, 10, 11, 12, you're going to repeat the same pattern, and so forth. So you only got 4 possibilities for values for powers of I. So let's look at number 5. So I'm going to distribute that 3 to the 6 and then also to the I. So that's going to be 6 cubed times I cubed. 6 cubed is 216, and I cubed is -I. So if I multiply that out, I'm going to get -216I. Now let's look at I to the 55th power. So the way I do this is I take that 55 and I divide it by 4. So if I divide 55 by 4 on the calculator, I get 13.75. And you could pick a bunch of numbers and divide them by 4. And you'll find out that you always get one of 4 decimal parts, the part to the right of the decimal. You'll get either 0.25, 0.5, 0.75, or a whole number, so I'm going to say 0. So the pattern is, if the portion to the right of the decimal is 0.75, you've got I cubed. If it's 0.5, you've got I squared. If it's 0.25, you've got I. And if it's 0, a whole number, you've got I to the fourth. And you could prove this if you write out your powers of I all the way to I to the 55th. You'd find out that I to the 55th is going to land on the negative I part of the pattern. All right, so this works, and it's all based on a repetitive pattern of 4. Okay, and you can write out a table if you don't believe me. But if you divide your power by 4 and look at the part to the right of the decimal, it's going to be like, you can think about this in terms of money even. A quarter, 2 quarters, 3 quarters, and 4 quarters. 25 cents, 50 cents, 75 cents, $1. So the part to the right, if it's 0.25, your answer is I. And then so forth. Using this table right here, it works. So I to the 55 is equivalent to I cubed, which is negative I. All right, now let's try it with 1066. So try it yourself. Take your calculator out, divide 1066 by 4, and see what your part to the right of the decimal is. Okay, so did you get 266.5? So the part to the right of the decimal is 0.5. You should have gotten that. So that means that your answer is I squared. So this is I squared. I squared is negative 1. Okay, so you want to write this table that I just drew a square around in your notes under Powers of I, section 3.4, and make a note to yourself that you divide your power by 4, and whatever that ending part is will give you the equivalent power of I. So if your ending part is 0.25, your answer is I, and so forth on down the line. Okay, next part, review, is what is meant by the conjugate of a complex number. So the conjugate is formed by changing the middle sign. So we only change one sign, the middle sign, no other signs. All right, so if I'm in number 1 forming the conjugate of 4 minus 8i, it's 4 plus 8i. Number 2, the conjugate of 2 plus 5i is 2 minus 5i. Now there's reasons for doing this, and this is to help us simplify fractions that have i's in the denominator. So let's do number 3. This says multiply 3 plus 2i by its conjugate and simplify the result. So I'm going to take 3 plus 2i. I'm going to multiply it by the conjugate 3 minus 2i. So this is double distributing. So this is 3 times 3 minus 2i plus 2i times 3 minus 2i. So this is equal to 9 minus 6i plus 6i minus 4i squared. And this always happens that the two middle terms are going to be equal and opposite, so they cancel each other out. And your last term here is going to have an I squared, which is negative 1, which will then multiply by your negative 4 and turn that into a positive 4. So we're going to end up with a real number result. 9 plus 4 is 13. So multiplying a complex number a plus bi by its conjugate a minus bi results in a real number. And that's how we remove an I from the denominator to reduce a fraction that has an I in the denominator. So that leads us to division of complex numbers. So in number 1, I've got 2 divided by 5i. So you reduce complex fractions by removing the I from the denominator. So I need to get this I out of the denominator in order to consider this a reduced fraction. So I'm going to multiply by I over I. And what's going to happen, I'll have 2i in the numerator and 5i squared in the denominator. So that's equal to 2i times I squared is negative 1, so that's negative 5. So this is negative 2i over 5, or you could write it as negative 2/5 I. So negative 2/5 is the coefficient of the imaginary part of the complex number. So in this one, A is 0, B is negative 2/5. Okay, so let's do it again for number 2. I'm going to multiply by I over I to remove that I from the denominator so I can call this reduced. So I'm going to say I've got to distribute I times 2 minus 3I on the top. And then I've got 5I squared on the bottom. We know that's a negative 5. So on the top I've got 2I minus 3I squared divided by negative 5. So that's 2I. On the top I've got an I squared. This is a negative 1. Negative 1 times negative 3 would make that positive 3. And I've got a negative 5 on the bottom. So you're going to go ahead and put the negative 5 under each of these so you can separate out the two real and imaginary parts. And convention says that you write the A part first, so that's the real part, and the imaginary part second. All right, so that's your complex number. Okay, so this example here says I've got a binomial on top of a binomial, so those are more work. So if the denominator has a real and an imaginary part, you multiply the numerator and the denominator by the conjugate of the denominator, and that will remove the I from the denominator. So let's see how this works. So I'm going to multiply by the conjugate of the denominator, so that would be minus 3 plus 4i over minus 3 plus 4i. So we're multiplying by 1. Whenever the numerator and the denominator are the same value, that fraction is equal to 1, which won't change my original fraction. So that has to be same, top, bottom. So I'm going to go ahead and do my double distributing. So I've got 2 minus 3i multiplied by negative 3 plus 4i on the top. And I've got negative 3 minus 4i multiplied by negative 3 plus 4i on the bottom. All right, so let's carry this out. So we've got on the top 2 times minus 3 plus 4i minus 3i times minus 3 plus 4i. On the bottom, negative 3 times minus 3 plus 4i minus 4i times negative 3 plus 4i. Okay, I've got a lawnmower outside my window, but I'm going to keep recording. So I'm just going to distribute here. So that's the numerator. And that's the denominator. So I just did the distributing. Okay, so now I'm going to find my I squareds. There's 1, so that's a negative 1. There's 1, so that's a negative 1. So that means I've got, on the top, combine my reals, I got negative 6 plus 12, so that's 6. Combine my imaginaries, I have 8 plus 9, that's 17. All right, that's my numerator. Now on the bottom, combine my reals. Well, wait a minute, let's cross out the two middle terms first. Negative 12i plus 12i, and then combine my reals. I've got 9, this would be plus 16. 9 plus 16 is 25. Okay, now we're going to write it as a plus bi, so that means I'm going to put my 25 under the 6, that's my a. And then I'm going to put my 25 under the 17 and then write I. So that's A plus BI. That's the form of a complex number. So as you can see, we got the I out of the denominator. Okay, the last part of our review here is solving quadratic equations which end up with I's in the result. So let's take a look at the first one here. So I know I'm not factorable, so you can tell when you're factorable if 1 times 4 is 4, so I can make 4 1 times 4 or 2 times 2. If I need to get 3 in the middle there, I would need a negative number, not 2 negative numbers, and that's not possible given that 1 times 4 has to be positive 4. So it's not factorable, so that means I got to use the quadratic formula. All right, so let's identify A, B, and C. So A is your 1, B is 3, C is 4. And we're going to solve the equation x squared plus 3x plus 4 equals to 0, and that'll give you your zeros. So that means x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So that's negative 3 plus or minus the square root of 9 minus 16 over 2, which is negative 3 plus or minus the square root of negative 7 over 2, which is equal to negative 3 plus or minus the square root of negative 1 times the square root of 7 over 2. So that's negative 3 plus or minus I square root of 7 over 2. All right, now let's go ahead and write it in as 2 zeros. So one of the zeros is going to be minus 3 over 2 plus I times root 7 over 2. All right. Sometimes you're going to see that I on the other side, and I think that's how they do it in this software that is used for our homework problems, like this. So that's A plus BI, and then you give it a comma. I'm going to list the other zero. So it'd be negative 3 over 2 minus root 7 over 2I. Okay, so just showing you how the software that we're using lists your zeros and a list with a comma in between, and with the 2 under the 3 giving you the real part, and the 2 under the root 7 giving you the coefficient of the imaginary part. So those are the zeros. Okay, let's go on to number 2. So we're going to solve for the zeros. So we solve the equation 2x squared minus 9x plus 11 is equal to 0, and we find the x values that cause it to be 0. To do that, since this is not factorable, we're going to use the quadratic formula. So we've got A, B, and C. So writing it out, we've got our zeros are going to be our x's, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's going to be 9 plus or minus the square root of 81 minus 88 divided by 4. So that's 9 plus or minus the square root of negative 7 over 4. So we can just say this is 9 plus or minus I square roots of 7 over 4. So let's go over to here. So we're going to put the 4 under each piece. And now I'm going to write it as 2 separate zeros. So I'm going to say 9/4 plus root 7 over 4i is 1 0, and 9/4 minus root 7 over 4i is the other 0. So I wrote them in the list in A plus BI form. So these are your zeros. So this is the end of part 1, which is a review of what we learned in Algebra 2 about complex numbers. And the next part is going to be about how to find the zeros of higher order polynomials with a degree larger than 2, 3, 4, 5. So I hope you took good notes so that you can use them for solving the problems in the homework set and for the quizzes and the tests, which are open book.